Hi guys, and welcome back to Stranger Than Fiction. Today I want to tell you a little about everybody's favorite scientist, Albert Einstein. First, two quick questions about him. First question, did Albert Einstein ever receive a Nobel Prize? If you said yes, you're absolutely right. Einstein won the Nobel Prize for Physics in 1921. So question number two, what theory did he propose that got him the Nobel Prize? If you said the theory of relativity, believe it or not, you're actually wrong about that. Nowadays, Einstein's most famous for the theory of relativity, but before he developed that, he worked on some other tricky physics problems, including capillary action and the way particles move around in a fluid. Another problem he worked on is called the photoelectric effect, and his theory of how it works is actually what he won the Nobel Prize for. Like a lot of good ideas, it's amazing how simple it is. So what is the photoelectric effect? Well, back in 1887, Heinrich Hertz, the same guy whose name pops up in words like kilohertz and megahertz when we talk about frequency, Heinrich Hertz noticed that if you shine ultraviolet light on an electrode, it'll make electrical sparks more easily. Basically, the light knocks off electrons from the metal in the electrode, and the electrons cause the sparks that you see. That doesn't sound too hard to understand, but if you actually start doing experiments, you find out that the photoelectric effect doesn't behave the way you might expect it would. Now, even back then, they knew that light was a wave, so they figured a light wave would act something like a sound wave. So, for example, let's say you wanted the electrons to come off the metal moving faster. In that case, you'd hit them with more energy. Now, if the wave was a sound wave, the way you'd make it have more energy is by increasing the amplitude. Basically, you'd make the sound louder. So they thought that the same thing would happen if you increase the amplitude of a light wave. If you make a light wave's amplitude higher, you do that by making the light brighter. But if you make the light brighter, that's not what happens. If you make the light brighter, it doesn't change the speed of the electrons at all. Instead, you just get more electrons coming off the metal. Another odd thing happens if you change the frequency of the wave. Now, if it were a sound wave, you wouldn't think changing the frequency would have any effect on the way electrons come off the metal, because the sound wave has the same amount of energy no matter whether it's tuned to a middle C, or an A, or an F sharp, or whatever it is. So they thought if you changed the frequency of the light wave, which you do by changing the color, it shouldn't do anything to the energy of the electrons. But that's not really what happens. It turns out the electrons that come off have more energy if you have a higher frequency of light. So if you lower the frequency, the electrons come off slower. And if you lower the frequency enough, you find out you don't get any electrons coming off the metal at all. So there were two surprising results. If you increase the intensity of the light, you don't get faster electrons, you just get more of them. And if you increase the frequency of the light, you get electrons that come off faster. These were both really surprising results. If you think of the waves as though they were like water waves crashing on a beach, and imagine that the electrons are like little grains of sand, increasing the height of the wave, the amplitude, would knock the sand grains farther. So it's surprising at first that increasing a light wave's amplitude doesn't give the electrons an extra kick. Also, if the water waves hit the beach more often, more frequently, they will make more sand move, but the individual grains don't actually go any faster. But that is what happens with light. If you increase the frequency, the electrons have more energy, and so they move faster. So why does all that happen? Explaining it was one of Einstein's biggest successes. Albert Einstein said, suppose instead of thinking of light as a wave, we imagine that it's a particle, which he called a photon. In that case, when you make a light brighter, what that means is you're emitting more photons, more light. So the photons hit the metal more often, and that's why they knock off more electrons. But each one still has the same speed that it usually does. That's exactly what we see when we make the light brighter. The electrons come off more often, but with the same speed as usual. Einstein also suggested that a light's color is a result of its energy. So a blue photon has more energy than a red one, an ultraviolet photon has more energy than the blue one, and so on. So the higher the frequency of the light, the more energy the photon has. And that's why the electrons that come off the metal have more energy when you increase the frequency of the light. It also explains why no electrons at all come off if you reduce the frequency too much. It takes a certain amount of energy to get the electron to come off at all, so if the frequency of the light is high, photons have more than enough energy to knock electrons off the metal. But if the frequency is really low, then they don't have enough energy. Einstein summed all that up in this short equation. E here is the energy of the electrons that come off the metal, and that's equal to this number. H times nu is the energy of the light. The Greek letter nu stands for frequency, so the higher the frequency, the more energy the light has. And h is a number called Planck's constant, which the physicist Max Planck had used earlier to explain blackbody radiation. I talked about that in an earlier video. This number is the Greek letter phi, and that's the threshold energy. It's the energy the light needs to have in order for an electron to get knocked off the metal. If the light has more energy than that, so that h nu is larger than phi, then the electron will come off the metal and it'll have energy E. The higher h nu is, the more energy the electron's going to have, so the faster it's going to move. But if h nu is less than phi, then E is going to be a negative number, which means the electron won't have enough energy to get away from the metal. So, why were all these ideas worth giving Albert Einstein a Nobel Prize? Well, first of all, although they didn't know it at the time, it turns out the photoelectric effect is really useful. It's important for solar energy, for example. A lot of solar cells use the photoelectric effect to change sunlight into electricity. The photoelectric effect is also used in night vision glasses. Infrared light that comes off a person's body hits the glasses, and that causes an electric current, which you can see. But even more important than those applications was Einstein's basic idea, the idea that light can behave like a particle called a photon. Now, hundreds of years earlier, other scientists like Isaac Newton also thought that light might be made of particles. Newton called them corpuscles. But by Einstein's time, that idea had kind of faded away, and most people thought that light was just a wave. Einstein's idea that light can come in little pieces was a big step in the creation of quantum mechanics. But that also raises a question. What is light, then? Is it a particle, or is it a wave, or is it neither one? I'll talk more about that in a new video pretty soon, and I hope you'll join me for it. Also, if you haven't seen my earlier video about Max Planck and blackbody radiation and why we care about them, I hope you'll give that video a look too. Thanks for watching!